Overview of operating systems. In this video, we are going to see about overview of operating systems. An operating system is a suite of programs which takes control of the operation of the computer to the extent of being able to allow a number of programs to be run on the computer without human intervention. It controls the way software use hardware. The purpose of this control is to make the computer operate in the way intended by the user and in a systematic, reliable, and efficient manner. It gives a brief overview of salient features of the operating system and different types of operating systems. Introduction to operating system concepts. In this video, we are going to see about Introduction to operating system concepts. An operating system, that is OS, is the backbone of every computer system. Any computer system can be divided into two major components, the hardware and the software. Software is further classified as system software and application software. Operating system is a part of the system software. It is difficult to have a definition that completely defines an operating system. An operating system can be defined as a program that acts as an interface between a user of a computer system and the hardware of the computer system. Operating systems govern the operation of hardware resources such as processors, main storage, secondary storage, input or output devices, and files. These modules try to optimize performance, resolve deadlocks and conflicts, and simplify the effective use of the system. The operating system is a program that, when in operation, ensures the smooth functioning of computer. For example, it performs the task of scheduling the use of the computer system resource. It increases the efficiency and consequently reduces the cost of using a computer system. Thus, the primary objective of an operating system is to make the computer system convenient to use and utilize computer hardware in an efficient manner. The positioning of the operating system in the overall computer system is given. Operating system terminology. Few terms that are commonly used in relation to operating systems are defined as follows. User. A user is anybody who desires work to be done by a computer system based on its instructions. Job. Job is a collection of activities needed to accomplish the required task. A job may be divided into several steps called job steps, which are units of work that must be executed sequentially. Process, that is task. It is a computation that may be done concurrently with other computations. Address space. The collection of programs and data that are accessed during execution of a process forms an address space. Address space can be for input or output processes, CPU processes, etc. The operating system must map the address space of processes into physical memory. This task is completed by the use of special hardware like page system, or may be performed primarily by software, that is, a swapping system. System calls. In this video, we are going to see about system calls. There are two ways in which users and application programs interact with the operating system. These are through the use of operating system calls in a program, through the use of operating system commands. The major difference between the two is that system calls are more fundamental as compared to the system commands. Commands are usually implemented as stand-alone programs, while system calls are used as C functions. System calls usually form a part of the core of the operating system. System calls provide the interface to a running program and the operating system. A user program invokes operating system services using the set of system calls available. Earlier, these calls were written in assembly languages, but nowadays these are implemented as high-level language functions. For example, suppose we want to write a program using system calls that takes file name as an argument and prints its contents on the terminal screen. First, the program has to establish a connection between itself and the file. This job is called opening a file. Then extracting information from a file is called reading a file. The program needs to output the file contents on the terminal. Therefore, the special file that describes the terminal also needs to be opened. Next, writing information previously read to the terminal is required. Finally, the program has to close several connections from the file and terminal, called closing the file. System calls can be written to open, read, write, and close files. The same job could be performed by an operating system command. For example, the above job could be performed through the cat command available in Unix. Types of operating systems. In this video, we are going to see about types of operating systems. Historically, operating systems have evolved from the most basic serial processing operating system to the sophisticated distributed operating system. Major features of different types of operating systems can be studied in terms of processor scheduling, memory management, input or output management, and file management. Serial processing operating system. Programming of the bare machine was customary for early computer systems. With the advent of input or output devices such as punched cards, paper tapes, and language translators came in a new era of computer system usage. Programs coded in higher programming languages are translated into executable form by a computer program. A loader then automates the process of loading executable into memory. Control is transferred automatically or manually to be loaded program, and execution commences. Due to the serial execution of programs, the development and execution of these programs is quite slow and cumbersome. Even with tools like editors and debuggers added, program development is very slow and involves manual program and data loading. Batch operating systems. Batch processing allows little direct interaction between users and executing programs. Thus, programs that require less interaction and long execution times like the payroll forecasting programs are suitable or batch operating systems. Batch processing automates the sequencing of operations involved in program execution. Scheduling in batch systems is very simple as jobs are processed on first come, first serve basis. Memory management is simple as the memory is divided into two parts, one for the resident portion of OS and the other for loading transient program for execution. File management is simple since access to files is serial. The elapsed time between job submission and job completion is called turnaround time. The batch processing, due to speed mismatch between the CPU and input-output devices, CPU remains idle for long durations. Spooling is used to overcome this disadvantage to some extent. Spooling is a technique which uses the disk as a huge buffer for reading as far ahead as possible on input devices and storing output files until the output devices are able to receive them, and it thus essentially overlaps the input or output of one job with the computation of other jobs. Multiprogramming operating systems. Buffering and spooling improve system performance by overlapping the input, output and computation of a single job, but both of them have their limitations. A single user cannot always keep the CPU or input-output devices busy at all times. Multiprogramming offers a more different approach for increasing system performance. In order to increase the resource utilization, systems supporting multiprogramming approach allow more than one job that is programmed to utilize the CPU concurrently. Multiprogramming operating systems need to deal with multiple users, therefore they are more complex. They need job scheduling algorithms to choose among several jobs, the next job to execute, memory management as several programs are in the memory at the same time, CPU scheduling to choose between several jobs ready to run at the same time. The operating system needs to have the ability to coordinate and limit the effects of multiple jobs running concurrently on each other. Multiprogramming systems extend support to both multitasking and multi-users. Multiprogramming implies multitasking but not vice versa. In multi-access operating systems, two or more terminals can be accessed simultaneously through a single program. Example is an airline ticket reservation system that supports hundreds of active terminals across many cities under the control of a single program. Multiprocessing OS manages the operation of computer systems that incorporate multiple processes. Multiprocessing systems are inherently multitasking systems. Time-sharing operating systems. Time-sharing or multitasking is an inherent extension of multiprogramming. Multiple jobs are executed by the CPU switching between them with minimum delay, and thus providing each user the illusion of doing only their work. It is an online system. The user is able to access both data and code conveniently. This is facilitated by an online file system. Time-sharing systems were developed mainly to provide interactive use of a computer system. It uses CPU scheduling and multiprogramming to provide each user with a small portion of a time-shared computer. This time portion is called a time slice. Time-sharing operating systems are more complex than the multi-programmed operating systems. Complex memory management is required as several jobs must be kept simultaneously in memory. Jobs need to be swapped in and out of main memory to disk to give a reasonable response time. Virtual memory is a technique through which this is achieved. To ensure orderly execution and CPU scheduling, the system must provide mechanisms for job synchronization and communication and deadlock avoidance. File management must provide protection and access control as well as sharing of files. Multiprogramming and time-sharing form the core of the modern operating systems. Nowadays, almost all operating systems are written in a higher level language, that is C, Pascal, etc. Unix is an example of the first operating system developed in C language. This feature improves their implementation, maintenance, and portability. Linux has brought Unix-like operating system to personal computers. Real-time operating systems. In computing environments where a large number of external factors have to be taken into consideration and acted upon within short time duration or deadlines, real-time operating systems are required. The real-time systems aim at providing quick event response time. Multiprogramming alone cannot meet the demands of a real-time operating system. Explicit programmer-defined and controlled routines must be available in a real-time system. A separate process is required for handling a single external event. The process is activated when the related event occurs, which is often signaled by an interrupt. It uses a priority-based preemptive scheduling. Memory management is comparatively straightforward than in other types of multiprogramming operating systems. This is because many processes permanently reside in the memory to provide quick response time. There is a requirement for both separation and sharing of memory. The processor in real-time systems is normally allocated to the highest priority process among those which are ready to execute. Time is most critical in real-time systems. Distributed operating systems. A distributed operating system is one that appears to its users like an ordinary centralized operating system, but runs on multiple independent CPUs. A collection of independent computer systems communicate and cooperate among themselves via hardware and software interconnections, creating a network. Users need not be bothered about how the resources are shared. Distributed operating systems involve the system-wide sharing of resources, files, and input or output device. They should support additional services of remote access to resources, communication with remote processes, distribution of computations with the use of global naming, distributed file system, inter-node process communication, and remote procedure calls. Advantages. There are three important advantages in the design of distributed operating systems. Major breakthrough in microprocessor technology, incremental growth, reliability. Major breakthrough in microprocessor technology. Microprocessors have become very powerful and cheap compared to the mainframes and mini-computers, so it has become attractive to think about designing large systems consisting of a number of small processors. These distributed systems clearly have a price or performance advantage over more traditional systems. Incremental growth. The second advantage is that there is a need of 10% more computing power. One should just add 10% more processors. System architecture is crucial to the type of system growth, since it is hard to give each user of a personal computer another 10% capacity. Reliability. Reliability and availability can also be big advantages. Few parts of the system can be done without disturbing users using the other parts. On the other hand, unless one is very careful, it is easy for the communication protocol overhead to become a major source of inefficiency. Process management. In this video, we are going to see about process management. The concept of process, which is central to the understanding of today's computer systems that support multiprogramming. The concept of discrete process state, transitions between these states, process hierarchies, process scheduling algorithms, and threads. Operating system components. A complex system like an operating system is created by dividing the whole system into smaller components which have well-defined inputs, outputs, and functions. A general set of such components includes process management, file system management, system calls, user programs, hardware, memory management, and the like. An operating system provides a number of services. At the lowest level, there are system calls which allowing a running program to make a request from the operating system directly. At a higher level, there is the command interpreter, which supports a mechanism for a user to issue a request without writing a program. Process management. Process management manages the allocation of processes, that is, tasks or jobs, to a processor. The concept of process is central to the understanding of operating systems functioning. Therefore, it is very important to understand and appreciate this concept fully. Process. In a multiple program environment, a single program does not have complete control of the system. This gave rise to the concept of process. Process is a program in execution, like a time-shared user program is a process, spooling output to a printer is a process. A process is an executable part of a program. A process is much more than just the program code called the text section. With every process, a stack is also associated. A stack maintains temporary data of global variables, a program counter which marks the next instruction to be executed, and the contents of process register. The main difference between a program and a process is that a program is a passive entity, whereas a process is an active entity. The program counter and a set of associated resources make a process an active entity. The execution of a process is sequential, that is, at any time, at most one instruction is executed on behalf of the process. Two processes may share the text section but will have separate stack and data sections. For example, a user may be running several copies of the editor program, or several users may be running copies of the mail program. In these cases, the text sections for the editor program or the mail program are equivalent, but the associated data sections will be different. A process many a times spawns many processes as it runs. Process states. As a process executes, it changes many states. The state of a process is defined by the current activity of that process. The major states in which a process can be at any instant are new, ready, running, suspended, terminated. When the process is being created, the process is waiting to be assigned to a processor. Instructions are being executed. The process is waiting for some event to take place. The process has finished execution. When a process is temporarily suspended, it is required that information about it be stored in a memory location so that its execution could start from the same status from where it was suspended. All this information forms the state variables, which are usually stored in a data structure called a process table. Operating system also provides several system calls to manage processes. Process hierarchies. Operating systems need ways to create and kill processes. When a process is created, that is, for example, in Unix OS, it is done using fork system call. It further creates more processes and so on, thus forming a process hierarchy, that is parent-child relationship or process tree. One of the processes acts as a parent to all other processes. That is, in Unix, it is the init process. Process implementation. Each process is represented in the operating system by a process control block, that is PCB, which contains information associated with a specific process. Process number, priority, process state, program counter, registers, accounting, input or output status, file management, processor scheduling details, memory management information. Process number. Each process is identified by its process number called Process Identification Number, that is PID. Priority. Each process is assigned a certain level of priority that corresponds to the relative importance of the event that it services. Process state. Each process may be in any of the following states: new, running, suspended, terminated. Program counter. It is the address to the next instruction to be executed for this process. Registers. There are many types of registers used by a process. These include the accumulator, general purpose registers, index registers, etc. Whenever a processor switches over from one process to another process, information about the current status of the old process is saved in the registers along with the program counter so that the process be allowed to continue correctly afterwards. Accounting. This includes actual CPU time used in executing a process in order to change individual uses for processor time. Input or output status. It includes outstanding input or output request, allocated devices information, pending operations, and so on. File management. It includes information about all open files, access rights, etc. Processor scheduling details. It includes a priority of a process, address to scheduling queues, and any other related information. Memory management information. This includes the value of base limit registers, the page tables, or the segment tables depending on the type of memory system used by the operating system. CPU passes control when multiple processes are running. The PCB is thus a repository for any information that may vary from process to process. Once constructed for a newly created process, the PCB is filled with programmer-defined attributes. Other values are assigned default values. All this information helps in hardware state being restored during changes in process states. Multitasking operating system is essentially event-driven, that is, they perform operations in response to systems events that can state changes and can lead to a resources reassignment. In an operating system, it is essential to ensure that the system is informed about each event and thus enabled to process properly the changes of global system state. Events may be internal, such as sending and receiving signals, or may be external, such as completion of input or output operation. External events usually synchronous and occurs as a side effect of the execution of OS system calls invoked by the running process. Process context switch. Switching the CPU to another process involves saving the status information of the old process and loading the saved state for the new process. During context switch, the system does no useful work as such. Thus, it is a pure overhead. Context switch times are highly dependent on hardware support. Context switching has become a performance bottleneck as many advanced memory management techniques require extra data to be switched with each context. The efficiency of context switching is increased by providing new structures called threads. Scheduling. In this video, we are going to see about scheduling. A single processor may be shared among several processes, with some scheduling policy being used by the OS to allocate one process and deallocate another one. Scheduling is a fundamental operating system function. Scheduling refers to a set of policies and mechanisms built into the operating system that define the order in which the computer system works. A scheduler is a part of the operating system that selects the next job to be admitted into the system for processing. The main objective of the scheduler is to optimize system performance through higher throughput and better CPU utilization. Throughput is the amount of work accomplished in a given time interval. There are basically three types of schedulers: long-term, medium-term, and short-term schedulers. This categorization is based on the operating environment, objectives, and relationship to other schedulers. Processes on entry in the system are put into a job queue. Queue is a list or data structure with a first in, first out principle. A job queue, thus, has all processes present in the system. The processes that are in the main memory and are ready and waiting to execute are kept on a list called the ready queue. A ready queue is implemented as a linked list. There are other queues like the device queue, which contains processes waiting for a particular input or output device. The long-term scheduler, also called the job scheduler, selects processes usually from the disk, where system processes are often spooled in a batch for later execution. The long-term scheduler loads such processes into the memory for execution. The short-term scheduler or CPU scheduler selects processes from the main memory that are ready to execute and allocates the CPU to one of them. A short-term scheduler has to operate a lot more frequently than a long-term scheduler because a process may execute for only a few milliseconds before wanting an input or output operation. Often, short-term scheduler executes at least once every 100 milliseconds in contrast to intervals of maybe minutes in a long-term scheduler. Short-term schedulers must thus be very fast. Long-term schedulers can be slower because the interval between creations of processes in the system may be in minutes. So, the scheduler can afford to take more time to decide which process should be selected for execution. The jobs can be input or output bound or CPU bound. An input or output bound process spends more time doing input or output, and a CPU bound process generates input or output requests infrequently using more CPU time. The long-term scheduler has the responsibility of maintaining a balance between selecting input or output bound and CPU bound processes so as to optimize the use of the CPU and input or output devices. Sometimes sharing systems introduce an additional level of scheduling called the medium-term scheduler. In a system, it is sometimes advantageous to remove processes from the main memory and thus reduce the degree of multiprogramming, then reintroduce the process into memory when required and continue its execution from where it was left off. This is called swapping. The medium-term scheduler is responsible for handling the swapped-out processes. However, once the suspending condition is removed, it attempts to allocate the required amount of main memory and swap the process in and make it ready. The medium-term scheduler requires information about the memory requirements of swapped-out processes. A scheduler's performance is measured in terms of processor utilization, throughput, turnaround time, waiting time, and response time. Scheduling algorithms. In this video, we are going to see about scheduling algorithms. All the three types of schedulers can use preemptive or non-preemptive scheduling approach. In non-preemptive scheduling, the running process is not forced to relinquish ownership of the processor when a higher priority process becomes ready for execution, though it may get suspended due to its own input or output want. The various scheduling algorithms are discussed below. First come, first served, that is FCFS scheduling. Shortest job first, that is SJF scheduling. Priority-based scheduling. Round-robin scheduling. Multiple level queue, that is MLQ scheduling. Multi-level feedback queue scheduling. First come, first served, that is FCFS scheduling. This is the simplest algorithm in which the job is executed in order of its arrival. It is implemented as a FIFO queue. It is a non-preemptive algorithm but usually results in poor performance. Shortest job first, that is SJF scheduling. In this algorithm, the job having the shortest execution time is processed first, then the next shortest, and so on. If two processes have the same CPU time, then FCFS is used. It may be implemented as a preemptive or non-preemptive algorithm. In both cases, it searches the ready queue for the shortest execution time job. It tries to optimize the average waiting time of a given set of processes. The drawback is that the optimal performance of SJF scheduling is dependent upon future knowledge of the process behavior, that is, of its CPU burst. This problem can be reduced to some extent by using a sorted list of ready queue processes on the basis of their execution times. Round-robin scheduling. It is primarily used in time sharing and a multi-user system where the primary requirement is to provide reasonably good response times, and that too in a fair way. In this, the CPU is divided into time slices and each process is allocated a time slice, after which it is not completed. It is placed at the end of ready queue to await the next allocation. Otherwise, if the running process releases a control to operating system voluntarily due to input or output request or termination, another process is scheduled to run. Round-robin utilizes the system resources in a very balanced manner. Small processes may be executed in a single time slice, while some processes may take several time slices and thereby be placed at the end of the queue several times. For example, suppose there are three processes, say P1, P2 and P3, which require 25, 5, 5 CPU times respectively. If a time slice of 5 units of time is used, then P1 gets first 5 units of time, then is preempted and placed at the end of the queue. P2 gets the next time slice and finishes. P3 gets the next 5 units time slice and completes. Now P1 again gets the time slice and so on. The implementation of a round robin requires a dedicated timer. Processing the interrupt to switch the CPU to another process involves context switching. The scheduler itself simply stores the context of the running process and appends it to the end of the ready queue. Priority-based scheduling. In this approach, a priority is associated with each process and the scheduler picks up the highest priority process for execution from the ready queue. Equal priority processes are scheduled FCFS. The priority may be assigned in terms of resource requirements, process characteristics, and its runtime behavior. The disadvantage in this scheme is that a low priority job may have to wait for an indefinite long period of time to obtain the CPU time. To overcome this aging problem, priority is used. Aging priority is a technique of gradually increasing the priority of processes that is of low priority that wait in the system for a long time. Eventually, the older processes attain high priority and their completion is ensured in a finite time. Multiple level queue, that is MLQ scheduling. A multiple level queue scheduling algorithm partitions the ready queue into separate queues. Processes are permanently assigned to each queue based upon properties such as interactive jobs, batch jobs, memory sizes, and so on. Each queue has its own scheduling algorithm. One may be using PCPS, the other Roundrobin, and so on. There are different ways of managing queues. This can be to assign a time slice to each queue, which it can schedule among different processes in its queue. Foreground processes can be assigned 50% of CPU time, whereas background jobs are given 20% of the CPU time. Multiple level queues with feedback scheduling. In a multiple level queue scheduling algorithm, processes do not move between queues. Multi-level feedback queue scheduling allows a process to move between queues. The idea is to separate processes with different CPU burst characteristics. If a process is using too much CPU time, it will be moved to a low priority queue. This scheme leaves input or output bound and interactive processes in the higher priority queues. Similarly, if a process waits too long in a lower priority queue, it may be moved to a higher priority queue. Interprocess communication. In this video, we are going to see about interprocess communication. All processes can potentially execute in concurrent manner. Concurrency refers to parallel execution of a program. There are fundamentally two relations among concurrent processes: competition and cooperation. All concurrent processes compete with each other for allocation of system resources by virtue of sharing resources of a single system. In addition, a collection of related processes that collectively represent a single logical application often cooperate with each other. Both competition and cooperation of processes require proper OS support. Concurrent processes are the basis of operating system which supports multiprogramming. The operating system supports concurrent execution of a program without necessarily supporting elaborate form of memory and file management. This is known as multitasking. In order to cooperate, concurrently executing processes must communicate and synchronize. Interprocess communication is based on the use of shared variables or message passing. Synchronization is often necessary when processes communicate. Thus, one can view synchronization as a set of constraints on the ordering of events. Processes frequently need to communicate with other processes. Processes that are working together often share some common storage that one can read and write. Each process has a segment of code called critical section, which accesses shared memory or files. The key issue here is to find a way to prohibit more than one process from reading and writing the shared data at the same time. Threads. In this video, we are going to see about threads. Threads provide a software approach to improving performance of operating systems by reducing the overhead of process switching. A thread is a lightweight process with a reduced state. If a process has exactly one thread, then it is equivalent to a classical process. Each thread belongs to exactly one process. The state reduction is achieved by having a group of related threads share other resources such as memory and files. Threads take over the role of processes as the smallest individual unit of scheduling. For a collection of threads, processes become a unit of resource ownership such as memory and files. Typically, each thread represents a separate flow of control and is characterized by its own stack and hardware state. As all resources except the processor are managed by the enclosing process, switching between related threads is fast and efficient. If you switch between threads that belong to different processes, it involves a full process switch with its associated overhead. Threads provide a convenient way of exploiting concurrency within an application. Threads provide the benefits of speed and sharing to related threads that constitute a single application while providing full protection between different applications. Memory management. In this video, we are going to see about memory management. Memory is one of the most precious resources in a multi-programming environment. Memory management is primarily concerned with allocation of physical memory of finite capacity to requesting processes. There are many contiguous and non-contiguous memory allocation schemes. The files are the structure which are most visible to a system user. The file management component of the operating system manages data residing in secondary storage. Introduction to memory management. Memory is a coveted resource in a multi-programming system. Its effective utilization is a predominant factor in overall resource utilization and other performance criteria of a computer system in terms of both effectiveness of allocating memory and influence on the scheduler. Memory management is primarily concerned with the allocation of physical memory of finite capacity that is, however, large to requesting processes. Processes can only be activated after a certain amount of memory is allocated to them. In response to request issued by the memory manager, the basic input or output system performs operations to allocate portions of address spaces in primary and secondary memory. Various approaches to memory management can be based on either contiguous or non-contiguous allocation of memory. Example of a contiguous memory allocation scheme is swapping, and of non-contiguous memory allocation is paging. Non-contiguous allocation of memory implies that the memory is allocated in such a manner that parts of a single logical object may be placed in non-contiguous area of physical memory. Address translation that is performed during the execution of instructions establishes the required correspondence between a contiguous virtual address space and the possible discontiguous physical address spaces. Contiguous allocation, on the other hand, implies that each logical object is placed in a set of memory locations with consecutive addresses. The main requirement of memory management is to be able to meet two requirements: a separation of address spaces, that is, memory protection, and to allow sharing of memory to cooperating processes. These two conflicting requirements are adequately met by various memory management schemes. Contiguous memory allocation. In this video, we are going to see about contiguous memory allocation. The available physical memory is partitioned, and each free partition is made available to meet requests for memory. When a resident object terminates, its memory partition is freed and made available for allocation to another process. These partitions of the memory can be defined statically or dynamically. Both types of partitioning result in fragmenting the memory. Static partitions yield internal fragmentation. In this, memory is wasted in each partition where an object of smaller size than the partition itself is loaded. Dynamic partitions, though, overcome the problem of internal fragmentation by assigning the partition the size of the object. When an object is removed from memory, the partition it was in can now be assigned only to an object of the same size or smaller size. Over the long run, there comes a time when allocation fails to find a region to honor a request, even though combined size of free areas exceed the demand. This problem is called external fragmentation. If programs are relocatable, then potential efficiency of a memory manager is augmented. Relocatability, though, requires some sort of runtime hardware support to map the virtual program relative identifiers to the physical addresses where information items are stored at runtime. This added flexibility is a trade-off with reduction in performance cost by the additional operations involved in accessing memory. Different memory management schemes vary in relative complexity of address translation and thereby in the amount of related runtime overhead that they impose. For cases when all partitions are allocated, there are two options. One is postpone the loading of incoming process until a suitable partition can be allocated to it. The other is to force a memory resident process to vacate a sufficiently large partition. This produces an additional overhead of selecting a suitable process that can be replaced. This technique is called swapping and is discussed in the next section. Swapping. In this video, we are going to see about swapping. A process needs to be in the memory to be executed. Swapping is a process of removal of suspended or preempted processes from memory and their subsequent bringing back to memory. Swapping is beneficial in multiprogramming in systems which have limited memory capacity or little hardware support for memory management. Swapping is usually employed in memory management systems with contiguous allocation, fixed or dynamic partitioned memory, and segmentation. For an example of swapping, consider a multiprogramming environment with a round-robin CPU scheduling algorithm. As soon as quantum for a process ends, the memory manager will begin to swap out this process and swap in another process to memory space that has just been vacated. In the meantime, the CPU scheduler will schedule some other process already in memory for execution. Swapping thus always requires a backing store like disk to place swapped process on and get new process in. Generally, swap space is allocated as a separate chunk of disk separate from the file system so that its use is as fast as possible. The following figure illustrates a swapping process. The swapper, which is an operating system process, thus has major responsibilities such as selection of processes to swap out, selection of processes to swap in, allocation and management of swap space. A swapper performs most of the functions of the medium-term scheduler. The swapping of processes should be performed fast enough so that there are always processes in memory ready to execute, such that the CPU scheduler always has processes to schedule. On the other hand, the quantum must also be sufficiently large so that a reasonable amount of computing is done between swaps. For priority-based scheduling, the swapping policy is varied a bit to put up with removal of low-priority process on arrival of high-priority process. This variant is called roll-in, roll-out. If address binding is done at assembly or load time, then the swapped out process has to be swapped in the same memory space that it held previously. And if address binding is done at execution time, then it is possible to swap back a process into a different memory space, because the physical addresses are computed during execution time. The choice of the process to swap in is usually based on the amount of time it spent on secondary storage, priority, and satisfaction of the minimum swapped out disk residence time requirements. The system maintains a ready queue consisting of all processes whose memory images are on the backing store like disk or in memory and are ready to run. Whenever the CPU scheduler decides to execute a process, it checks to see whether the next process in the queue is in the memory. If it is not available and there is no free memory to upload it in, then the scheduler swaps out a victim process to adjust the process in the ready queue. It then reloads registers as normal and transfers control to the selected process. The context switch time in such a swapping system is fairly high. For efficient CPU utilization, we want our execution time for each process to be relative to the swap time. Suppose the user process is of size 100K and hard disk has a transfer rate of 1 megabyte per second, then it will take 1000K by 1000K per second is equal to 100 milliseconds to transfer 100K process. In a round-robin scheduling algorithm, the time quantum should be substantially larger than 0.216 seconds. The transfer time is directly proportional to the amount of memory swapped. Therefore, it will be advantageous to know how much memory a user process is using instead of how much it might use. There are other constraints on swapping, such as never to swap a process with pending input or output, to execute input or output operations only into operating system buffers. Transfer between operating system and process memory then occurs only when the process is swapped in. Currently, modified version of swapping is found on systems rather than the standard swapping, which requires too much swapping time and provides too little execution time to be a rational memory management solution. File concept. In this video, we are going to see about file concept. File system is the most apparent aspect of an operating system. File is a logical storage unit which provides the user abstraction from the physical properties of its storage devices. Files can be stored on any physical devices such as floppy disk, hard disk, magnetic tape, whose characteristics and organizations are different from each other. A file can be defined as a named collection of related information that is recorded on secondary storage. Files, from a user's perspective, provide a means to write to a secondary storage. File often appears as a sequence of bits, bytes, lines, or records whose meaning is defined by a programmer or user. Files are of several types, and if an operating system recognizes the type of a file, it can then operate on the file in reasonable ways. A binary file, if printed, produces garbage but can be prevented to do so if the operating system has been told that the file is a binary object program. A common way of implementing file types is to include the types as part of the file name, say as its extension. For example, in MS-DOS, files with extension .com and .exe are considered binary executable files, whereas BAT is an ASCII format file. The Unix program, however, does not use this extension convention. Instead, sometimes it uses a number stored at the beginning of some files to indicate roughly the type of the file. Though even this is not a set feature, not all files have numbers. Many times it is left to the application using the file to determine the file format. A file is defined by attributes like its name, type, location and size, protection and time, date of creation, last use, last modification and user identification. The information about all files is kept in the directory structure that also resides on secondary storage. Operations like creating a file, writing to a file, reading a file, repositioning within a file, deleting a file, truncating a file, updating a file, and a lot more are regularly performed on all files. File structure. In this video, we are going to see about file structure. File types are also used to indicate the internal structure of a file. There are three common file organizations. The first file organization is a simple byte sequence. The operating system does not impose any structure on the file organization. This type of scheme has been adopted in Unix operating system among others. Unix considers each file to be a sequence of 8 bits. No interpretation of these bits is made by the operating system. Each application program must incorporate its own code to interpret an input file into the appropriate structure. The advantage of this scheme is there is a maximum flexibility for the user, but the disadvantage is that there is no OS support. The second file organization is a sequence of fixed size records where arbitrary records can be read or written, but records cannot be inserted or deleted in the middle of the file. CP/M operating system supports this type of scheme. The third file organization involves usage of disk blocks. There can be n-keyed records in a disk block depending on the size of the block. All disk input or output are performed in terms of blocks. All blocks are equal size. Records can be searched by a key value and new records can be inserted anywhere in the file structure. However, all operating systems must support at least one structure, that of an executable file, so that the system is able to load and run programs. Internally locating an offset within a file can be a difficult job for the operating system. Different operating systems apply different schemes for this. For example, Unix operating system defines all files to be simply a stream of bytes. Each byte is individually addressable by its offset from the beginning or end of file. Here, a logical record is of 1 byte. The file system automatically packs and unpacks bytes into physical disk blocks. Directories. In this video, we are going to see about directories. Files grow speedily in numbers on all systems, and therefore An effective method is required to organize them for optimum output. This organization is implemented by a two-step method. Firstly, physical disk is logically divided into partitions which enable each disk to be treated as a separate disk. With this in effect, the user needs to be concerned only with the logical directory and file structure. Secondly, each partition contains information about files within it, organized in a tabular form called the device directory. The directory records file attributes like its name, location, size, and type for all files on that partition. The directory can be thought of as a symbol table that translates file names into the directory entries. The directory structure must be so designed so as to facilitate searching a file, creating a file, deleting a file, listing of a directory, renaming a file, and traversing the file system. A single flat directory can contain a list of all files in a system. Flat directories are those directories in which the root directory contains only all system and no subdirectories. Another structure of directory is a tree or hierarchical structure. In this, the collection of all directory and subdirectory entries define the totality of system files. Both these structures of directions, each file name must be unique, that is, test can be the name of only one file. Root has subdirectories exp, find, and here. The exp subdirectory further has a file done and a subdirectory s1. Names in circle indicate the file names, which are leaf nodes of a directory structure. Each file must have a parent directory. There can be only one root directory. Each file is recognized by a relative or absolute path name. Relative path can start from any directory above it, and absolute path starts from the root. Absolute path for the file B would be /exp/s1 and relative path would be exp/s1. The directory in which the user is presently working is called the current working directory. Parts of the directories are placed on secondary storage devices, as all of it in main memory would take up a lot of space, and all of it on secondary storage would result in large search times. Therefore, most systems resolve this problem by keeping directories on secondary storage devices and by copying only the actively used entries to main memory. The directory operations are primarily affected by the number of disks required to complete a search, to add, to remove an entry. Therefore, the internal structure of the directory should be such that this time is minimized. Hashing techniques support fast searching and appending operations. Disk allocation and access methods. In this video, we are going to see about disk allocation and access methods. An important function of the file system is to manage space on the disk in such a way as to provide effective utilization of disk space and fast accessing of files. Management of disk is similar to memory management, with two additional problems of slow disk access times and large number of blocks to deal with. Disk can be allocated files as contiguous or non-contiguous. The widely used allocation technique are contiguous, linked, and indexed, where the last two belong to non-contiguous allocation category. Contiguous allocation. Files are assigned to contiguous areas of secondary storage. A user requests a specified size of the area required to holding a file, and if this amount of contiguous space is not available, the file cannot be created. As all the successive records of a file are in contiguous memory locations, access is fast. Sequential access and direct access both can be easily used. For sequential access, the file system remembers the disk address of the last block and when necessary reads the next block. For direct access of a file, the block start and block number is read. Contiguous allocation of free disk space requires finding free contiguous blocks of required size. It uses schemes like first fit and best fit to provide the dynamic storage allocation. However, a major problem with contiguous allocation is the disk fragmentation that it produces. A combination of internal and external fragmentation occurs in varying degrees in first fit and best fit algorithms. After heavy usage, the problem affects the disk utilization acutely. Some compaction techniques can be implemented to reduce the effect of fragmentation. Linked allocation. As files change over the time, it is not easy for user to declare good approximations of their size, so non-contiguous allocation technique is used to accommodate this requirement. Linked allocation is an example of non-contiguous storage allocation. Linked allocation is basically a disk-based version of the linked list. Each file is a linked list of disk blocks which may be scattered throughout the disk. Some bytes of each block are reserved to hold address of the next block, that is link. The advantage of linked allocation is in its simplicity, as no disk compaction is required. Due to non-contiguous allocation, no external CK fragmentation takes place. A file can grow dynamically. The disadvantages of linked allocation are slow, direct accessing of any disk block as the pointer has to be followed sequentially, and space is wasted in maintaining pointers. The major problem is that loss of any pointer can result in making a large number of disk blocks inaccessible. Redundancy of pointer files is employed for safety recovery. Indexed allocation. Index allocation solves the problem of slow speed of direct accessing in linked allocation. By placing all of the pointers together into an index block, in this scheme, each file is provided with its own index block, which is an array of disk block addresses. The kth entry is the disk block points to the kth disk block of the file. To read the kth disk block, the pointer in the kth index block entry is followed to find the desired block. To accommodate large file sizes, indexing is done at different levels, that is, for a two-level indexing. The kth block may hold address of a block which instead of containing data contains addresses of n block. This can be extended to higher levels, the third level being the most frequent used technique. Higher levels result in more complexity. The advantages of indexed sequential scheme are absence of external fragmentation and easy implementation of direct access. The primary disadvantage is the number of disk accesses required to retrieve the address of the target block on disk. This overhead can be reduced by keeping frequently used index blocks in memory. The space requirement for pointer storage in indexed allocation is wrong than in linked allocation. Input and output hardware. In this video, we are going to see about input and output hardware. Computers operate on many kinds of devices. General types include storage devices, that is disk, tapes, transmission devices, that is network cards, modems, and human interface devices, that is screen, keyboard, mouse. Other devices are more specialized. A device communicates with a computer system by sending signals over a cable or even through the air. The device communicates with a machine via a connection point termed a port, that is, for example, a serial port. If one or more devices use a common set of wires, the connection is called a bus. In other terms, a bus is a set of wires and a rigidly defined protocol that specifies a set of messages that can be sent on the wires. Daisy chain. When device A has a cable that plugs into device B and device B has a cable that plugs into device C and device C plugs into a port on the computer, This arrangement is called a daisy chain. It usually operates as a bus. Controller. A controller is a collection of electronics that can operate a port, a bus, or a device. A serial port controller is an example of a simple device controller. The CSSI bus controller is often implemented as a separate circuit board, that is, a host adapter that plugs into the computer. It contains a processor, microcode, and some private memory to enable it to process the SCSI protocol messages. Some devices have their own built-in controllers. Input or output port. An input or output port typically consists of 4 registers called the status, control, data in, and data out registers. Status register, control register, data in register, data out register. Status register. The status register contains bits that can be read by the host. These bits indicate states such as whether the current command has completed, whether a byte is available to be read from the data in register, and whether there has been a device error. Control register. The control register can be written by the host to start a command or to change the mode of a device. For instance, a certain bit in the control register of a serial port chooses between full duplex and half duplex communication. Another enables parity checking. A third bit sets the word length to 7 or 8 bits, and other bits select one of the speeds supported by the serial port. Data in register. The data in register is read by the host to get input. Data out register. The data out register is written by the host to send output. Polling. Polling is a process by which a host waits for controller response. It is a looping process reading the status register over and over until the busy bit of status register becomes clear. The controller uses or sets the busy bit when it is busy working on a command and clears the busy bit when it is ready to accept the next command. The host signals its wish via the command ready bit in the command register. The host sets the command ready bit when a command is available for the controller to execute. In the following example, the host writes output through a port coordinating with the controller by handshaking. The host repeatedly reads the busy bit until that bit becomes clear. The host sets the wire bit in the command register and writes a byte into the data out register. The host sets the command ready bit. When the controller notices that the command ready bit is set, it sets the busy bit. The controller reads the command register and sees the write command. It reads the data out register to get the byte and does the input or output to the device. The controller clears the command ready bit, clears the error bit in the status register to indicate that the device input or output succeeded, and clears the busy bit to indicate that it is finished. Input or output devices. Input or output devices can be categorized into following category: human readable. Human readable devices are suitable for communicating with a computer user. Examples are printers, video display terminals, keyboard, etc. Machine readable. Machine readable devices are suitable for communicating with electronic equipment. Examples are disk and tape drives, sensors, controllers, and actuators. Communication. Communication devices are suitable for communicating with remote devices. Examples are digital line drivers and modems. Direct memory access, that is DMA. Many computers avoid burdening the main CPU with programmed input or output by offloading some of this work to a special purpose processor. This type of processor is called a direct memory access, that is DMA controller. A special control unit is used to transfer block of data directly between an external device and the main memory without intervention by the processor. This approach is called direct memory access, that is DMA. DMA can be used with either polling or interrupt software. DMA is particularly useful on devices like a disk, where many bytes of information can be transferred in single input or output operations. When used with an interrupt, the CPU is notified only after the entire block of data has been transferred. Interaction with the device controller is managed through a device driver. Handshaking is a process between the DMA controller and the device controller. It is performed via wires using terms DMA request and DMA acknowledge. A device driver is instructed to transfer disk data to a buffer address X. Device driver then instructs a disk controller to transfer data to buffer. Disk controller starts DMA transfer. Disk controller sends each byte to DMA controller. DMA controller transfers bytes to buffer, increases the memory address, decreases the counter C until C becomes 0. When C becomes 0, DMA interrupts CPU to signal transfer completion. Device controllers. A computer system contains many types of input or output devices and their respective controllers. Network card, graphics adapter, disk controller, DVD-ROM controller, serial port, USB, sound card. Input or output software. In this video, we are going to see about input or output software. Interrupts. The CPU hardware uses an interrupt request line wire which helps CPU to sense after executing every instruction. When the CPU checks that a controller has put a signal on the interrupt request line, the CPU saves a state such as the current values of the instruction pointer and jumps to the interrupt handler routine at a fixed address. The interrupt handler part determines the cause of the interrupt, performs the necessary processing, and executes an interrupt instruction to return the CPU to its execution state. The basic mechanism of interrupt enables a CPU to respond to an asynchronous event, such as when a device controller becomes ready for service. Most CPUs have two interrupt request lines: non-maskable interrupt, maskable interrupt. Non-maskable interrupt. Such kind of interrupts is reserved for events like unrecoverable memory errors. Maskable interrupt. Such interrupts can be switched off by the CPU before the execution of critical instructions that must not be interrupted. The interrupt mechanism accepts and addresses a number that selects a specific interrupt handling routine or function from a small set. In most architectures, this address is an offset stored in a table called the interrupt vector table. This vector contains the memory addresses of specialized interrupt handlers. Clocks. Clocks are also called timers. The clock software takes the form of a device driver, though a clock is neither a blocking device nor a character-based device. The clock software is a clock driver. The exact function of the clock driver may vary depending on operating systems. Generally, the functions of the clock driver include the following: kernel input or output subsystem. Kernel input or output subsystem is responsible to provide many services related to input or output. Following are some of the services provided. Scheduling. Kernel schedules a set of input or output requests to determine a good order in which to execute them. When an application issues a blocking input or output system call, the request is placed on the queue for that device. The kernel input or output scheduler rearranges the order of the queue to improve the overall system efficiency and the average response time experienced by the applications. Buffering. Kernel input or output subsystem maintains a memory area known as a buffer that stores data while they are transferred between two devices or between a device with an application operation. Buffering is done to cope with a speed mismatch between the producer and consumer of a data stream, or to adapt between devices that have different data transfer sizes. Caching. Kernel maintains cache memory, which is region of fast memory that holds copies of data. Access to the cached copy is more efficient than access to the original. Spooling and device reservation. A spool is a buffer that holds output for a device, such as a printer, that cannot accept interleaved data streams. The spooling system copies the queued spool files to the printer one at a time. In some operating systems, spooling is managed by a system daemon process. In other operating systems, it is handled by a kernel thread. Error handling. An operating system that uses protected memory can guard against many kinds of hardware and application errors. Security. In this video, we are going to see about security. Security refers to providing a protection system to computer system resources such as CPU, memory, disk, software programs, and most importantly, data or information stored in the computer system. If a computer program is run by an unauthorized user, then he or she may cause severe damage to computer or data stored in it. So, a computer system must be protected against unauthorized access, malicious access to system memory, viruses, worms, etc. Authentication. One-time passwords, program threats, system threats, computer security classifications. Authentication. Authentication refers to identifying each user of the system and associating the executing programs with those users. It is the responsibility of the operating system to create a protection system which ensures that a user who is running a particular program is authentic. Operating systems generally identifies or authenticates user using following three ways. Username or password. User needs to enter a registered username and password with operating system to log in into the system. User card or key. User need to punch card in card slot or enter key generated by key generator in option provided by operating system to log in into the system. User attribute, fingerprint or eye retina pattern or signature. User need to pass his or her attribute via designated input device used by operating system to log into the system. One-time passwords. One-time passwords provide additional security along with normal authentication. In one-time password system, a unique password is required every time user tries to log in into the system. Once a one-time password is used, then it cannot be used again. One-time password is implemented in various ways. Random numbers. Users are provided cards having numbers printed along with corresponding alphabets. System asks for numbers corresponding to few alphabets randomly chosen. Secret key. User is provided a hardware device which can create a secret ID mapped with user ID. System asks for such secret ID which is to be generated every time prior to login. Network password. Some commercial applications send one-time password to user on registered mobile or email which are required to be entered prior to login. Program threads. Operating systems, processes, and kernel do the designated task as instructed. If a user program made these processes do malicious tasks, then it is known as program threads. One of the common examples of program thread is a program installed in a computer which can store and send user credentials via network to some hacker. Following is a list of some well-known program threads. Trojan horse. Such program traps user login credentials and stores them to send to malicious user who can later on log in to computer and can access system resources. Trapdoor. If a program which is designed to work as required have a security hole in its code and perform illegal action without knowledge of user, then it is called to have a trapdoor. Logic bomb. Logic bomb is a situation when a program misbehaves only when certain conditions met, otherwise it works as a genuine program. It is harder to detect. Virus. Virus, as name suggests, can replicate themselves on computer system. They are highly dangerous and can modify or delete user files, crash systems. A virus is generally a small code embedded in a program. As the user accesses the program, the virus starts getting embedded in other files or programs and can make system unusable for user. System threats. System threats refer to misuse of system services and network connections to put user in trouble. System threats can be used to launch program threats on a complete network called as program attack. System threats create such an environment that operating system resources or user files are misused. Following is a list of some well-known system threats. Worm. Worm is a process which can choke down a system performance by using system resources to extreme levels. A worm process generates its multiple copies where each copy uses system resources, prevents all other processes to get required resources. Worms processes can even shut down an entire network. Port scanning. Port scanning is the mechanism or means by which a hacker can detect system vulnerabilities to make an attack on the system. Denial of service. Denial of service attacks normally prevents user to make legitimate use of the system. For example, user may not be able to use internet if denial of service attacks browser's content settings. Graphical user interface. In this video, we are going to see about graphical user interface. Graphical user interface provides the user graphical means to interact with the system. GUI can be a combination of both hardware and software. Using GUI, user interprets the software. Typically, GUI is more resource consuming than that of CLI. With advancing technology, the programmers and designers create complex GUI designs that work with more efficiency, accuracy, and speed. GUI elements. GUI provides a set of components to interact with software or hardware. Every graphical component provides a way to work with the system. A GUI system has following elements such as window, an area where contents of application are displayed. Contents in a window can be displayed in the form of icons or list if the window represents file structure. It is easier for a user to navigate in the file system in an exploring window. Windows can be minimized, resized, or maximized to the size of the screen. They can be moved anywhere on screen. A window may contain another window of the same application called child window. Tabs. If an application allows executing multiple instances of itself, they appear on the screen as separate windows. Tabbed document interface has come up to open multiple documents in the same window. This interface also helps in viewing preference panel in application. All modern web browsers use this feature. Menu. Menu is an array of standard commands grouped together and placed at a visible place that is usually top inside the application window. The menu can be programmed to appear or hide on mouse clicks. Icon. An icon is a small picture representing an associated application. When these icons are clicked or double-clicked, the application window is opened. Icon displays application and programs installed on a system in the form of a small pictures. Cursor. Interacting devices such as mouse, touchpad, digital pen are represented in GUI as cursors. On-screen cursor follows the instructions from hardware in almost real time. Cursors are also named pointers in GUI systems. They are used to select menus, windows, and other application features. Application-specific GUI components. A GUI of an application contains one or more of the listed GUI elements. Application window, dialog box, text box, buttons, radio button, checkbox, list box, application window. Most application windows uses the constructs supplied by operating systems, but many use their own customer-created windows to contain the contents of application. Dialog box. It is a child window that contains message for the user and request for some action to be taken. For example, application generate a dialog to get confirmation from user to delete a file. Text box provides an area for user to type and enter text-based data. Buttons. They imitate real-life buttons and are used to submit inputs to the software. Radio button displays available options for selection. Only one can be selected among all offered. Checkbox functions similar to list box. When an option is selected, the box is marked as checked. Multiple options represented by check boxes can be selected. List box provides list of available items for selection. More than one item can be selected. Other impressive GUI components are sliders, combo box, data grid, drop-down list. Device driver. In this video, we are going to see about device driver. Device driver is a program or routine developed for an input or output device. A device driver implements input or output operations or behaviors on a specific class of devices. For example, a system supports one or a number of multiple brands of terminals. All slightly different terminals may have a single terminal driver. In the layered structure of input or output system, device driver lies between interrupt handler and device-independent input or output software. The job of a device driver is following: to accept requests from the device-independent software above it, to see to it that the request is executed. A device driver handles a request is as follows. Suppose a request comes to read a block N. If the driver is idle at the time a request arrives, it starts carrying out the request immediately. Otherwise, if the driver is already busy with some other request, it places the new request in the queue of pending request.